Okay, so last time we have proved the following theorem due to Novikov that states that a complex Bordens ring is isomorphic to free polynomial algebra with one generator in each even degree. Yeah, and we have stopped here. So today we will go back to geometry, and we will describe more or less explicitly one family of stably complex manifold that represents the set of polynomial generators. So to do that, we have to start with the following theorem. So this is again theorem due to Novikov, and it describes the Milnor genus of polynomial generators here. Yeah, so the claim is following. So if we have element xi.
Что у тебя случилось? Почему у тебя такой экран?
В смысле, стандартный зумовский?
Да.
Ну, я как-то решил тут сегодня. А что, это плохо?
Или ты не смог просто?
Да нет, смог. Но я просто решил тут попробовать.
Ну просто тут, как бы я просто один раз не смог. Он у меня не дал просто расшарить как бы саму программу. Так, ну просто мне кажется, что твой почерк лучше в том редакторе. Он не так дрожит.
Я могу переключиться.
Ну, насколько тебе сложно?
Нет,
да,
я думаю, что не стоит. Ну что за ерунда? Семен, давайте не отвлекаться на такие вещи.
Окей.
Точнее так, Семен, если вам неудобно и это ощутимо, то тогда давайте переключимся. Ну, значит, давайте продолжим.
Давайте продолжим, хорошо. Yeah, so the theorem asserts the following things. So if we have stably complex manifold, then it can be taken as free polynomial generator in this ring. If and only if its Milnor genus is either P or 1, and this happens if I is P to the power T minus 1 for some T, for some prime P, and some T in wasn't 1 or 0, I'm sorry, and well, and 1 if it is not all this form. Yeah, so this is our first goal for today. So let's try to present the proof. So yeah, so first step here is the following. So we have to, well, I guess we kind of discussed, we have kind of discussed it, but okay, let me at least state the
Семен, just in case, do we already know what SI is?
I hope yes. Well, so this is
Okay.
Well, so yeah, if well, I guess we know, but I'm not sure about the.
Well, so I think it wouldn't do any harm to review the definition of SI.
It wouldn't be any harm. Yeah. Well, maybe.
Or ask the audience. Does anyone know or remember what SI of XI is?
Actually, it's important to remind what is SI denote, because there is difference between Young diagram and transposed Young diagram. So it's Newton polynomial or it's transposed version?
No, it is Newton polynomial.
Okay.
So SI. So suppose we have some. So what is SI actually? So we have. So it's suppose consider such symmetric polynomial, namely Newton polynomial, T1, Tn, sum of ith powers of Tj's. So this is a symmetric polynomial, and let's represent it in terms of elementary symmetric polynomials. So what should I write here? Maybe something like that. I1 to the power alpha 1, etc. IR to the power alpha R. Yes, and then SI is the following characteristic class, just the same sum of Chern classes instead of elementary symmetric polynomials. EIR.
Chern classes of which vector bundle?
Yeah, so in this case, well, so of given one. So in this case, this would be just Chern classes of the normal bundle, or then I guess I'm sorry, of the tangent bundle of Xi.
Okay, so so basically it's the power sums of the Chern roots of the stable tangent bundle.
Yes. Yeah. So yes. So yeah. So are there any other questions about the theorem, about the statement? Okay, so let's continue then. Yeah, so actually the only thing we need here is the following. Well, so to do that, first of all, we want to define these numbers in terms of some homomorphisms, and namely in terms of the Krevich homomorphism. So let me state the proposition. Yeah, so it says the following thing. So suppose we have complex kobordism ring. At the moment, we need we do not need the upper isomorphism, this one. so this would be just, actually this is more or less general statement, but let me state it just in case of complex kobordism. So we have Revich homomorphism from pi star of mu to homology of mu with integer coefficients. Yeah. Then we have the Thom isomorphism. With homology of B. Yeah, and as you remember, this guy, first of all, this guy is dual to cohomology. And the second statement that this guy is pre-polynomial algebra with, again, watch one polynomial generator in each even degree. Yeah, so yeah, and remark here that we can define SI is just dual to alpha 1 to the power I. So yeah, maybe we should left this as an exercise. Yeah, and proposition is the following. So we have map from here to here. And actually, this map can be described as follows. So we have stably complex manifold, and it sends to its set of characteristic numbers. Sum of how should I write this? Yeah, so maybe I should write this as follows. So we have yeah, so let me generalize this remark. So let us denote Sj as dual to alpha j, which is alpha 1 to the power j1, etc., alpha r to the power jr. Yeah, so this map sends this stably complex manifold into the following sum as over j of m, which is a number, times alpha j, sum through all g's. Yeah, I'm not sure if we have discussed it, and I'm not sure if we should discuss it.
Well, maybe briefly.
Yeah, so yeah, well, yeah. Then so this actually the proof is just kind of drawing some commutative diagram. So maybe I should just draw this diagram and let the details to audience. So this is a sketch. So consider the so we have the following diagram. Yes, so suppose again, so by our construction of Pendragon Thom isomorphism, so if we have stably complex manifold of dimension n, we embed it into Sn plus 2k, and then take, so, and then we have map f from Mn to B UK, whose, yeah, so yeah, that classifies the normal bundle in under the above embedding. Yeah, so now we can consider the following diagram. So we have homology, sorry, homology of sphere. We have Thom space of normal bundle. Or we've denoted by T of nu. I don't remember at the moment. So yeah, so let me just, so this is Thom space of, yeah, and new normal bundle. Yeah, and then we have morphism from here to homology of M U K. Yeah, and here we have two Thom isomorphisms. Sorry. And homology of M and homology of B U K. Yeah. So yeah, so we have this commutative diagram. So this is just projection onto Thom space. This is map induced by F. This is F star. Yeah, so we have this diagram, and one more thing that we should know here, that fundamental class from here maps to fundamental class of M. Yeah, if there is one. Yeah. So we suppose that M is orientable. Yeah, and the rest follows from this diagram. So we have to kind of go through this diagram and compute the characteristic numbers. Yeah, so is it enough, or more details should be shown?
Okay, does this diagram make any sense?
For me, yes, but yeah, but
Well, you've just drawn it. So the question is, does it make sense to the rest of us? Okay, well, let's assume it does.
Yeah,
Otherwise, otherwise, please, please let us know.
yeah, but actually the question was not about the diagram, but about the rest of the details. Should we present them or just move on?
Well, I think if the diagram itself makes sense, then the rest is straightforward.
Yeah.
Okay. If there are any people who don't understand what this is all about and what all the notation means, then please let us know. Otherwise, we just carry on.
Okay, so
Yeah, maybe I'm asking a stupid question, but does characteristic numbers of normal bundle determines characteristic numbers of tangent bundle?
yeah. Yeah, well, because characteristic classes of the
Yes, classes determined, but here we use only numbers. And in the beginning, we say that actually we're interested in as polynomials of tangent bundle. So we compute characteristic numbers of, say, tangent bundle. But in our original construction, we surely deal with the normal bundle. So question is, does this actually determines one each other?
The answer is yes, but yes.
So I mean, we really mean tangent characteristic numbers because we want something like standard formula for this S classes, and it's easy to deduce for product of, say, manifolds when we work with tangent bundle instead of normal. But this construction use only numbers, not all classes. So I just don't understand why there is one-to-one correspondence. Or maybe here we will assume that we compute characteristic numbers of normal bundle. I don't know.
Yeah, so actually, this is a very good question. So I thought that in the assertion of the of Novikov theorem, we should use the tangent bundle.
Yes.
But
yeah, right. Maybe it will become clear later. So, but this diagram and everything makes sense. But for
yes, yeah. So actually, if you consider just SI,
yes,
then of course the SI number of the tangent bundle and of normal bundle, I guess they are just one is a minus one of another one.
Mm. Okay. Yes, maybe.
Yeah, just because there's
Yeah.
trivial.
Okay. You're right. So the statement about polynomial generators is not sensitive to which bundle we speak of.
Yeah,
Okay.
yeah. So yeah, and actually there is a kind of yeah. So we add plus minus here. So this.
Okay. Okay, so we can check this either for normal or for a tangent bundle.
Yes.
Okay. Thanks.
Great. Yeah. So we reduced our question to description. So we just have to describe the Fourier homomorphism. Yeah, and it is clear that, well, we can describe it just Fourier homomorphism and not compose it with the Thom isomorphism. So just because it is isomorphism. Yeah, and yeah, it is the obvious one. So we have just to describe Fourier homomorphism from MU Bordism ring. I'm sorry, complex Bordism ring to homology of MU. Okay. Is it clear at the moment? So what we are going to do next? Okay, let's consider this answer yes. Yeah, so first step here is the following. So let's yeah, so we can, so if we consider the mod P Fourier homomorphism, then there is a yeah, then we have an Adam spectral sequence. Yeah, and there is a description in terms of the Adam spectral sequence. Suppose we have yeah, so this is general one. Suppose X is the spectrum of finite type. Then we have mod P Fourier homomorphism from pi star X to mod P homology of X. Yeah, and I claim that it factors through the atoms mod P atom spectral sequence as follows. We have from here to unity list. Then we can embed this guy. I'm sorry. Yeah, so let me just write it down first. Okay, so let's see what is going on here. Yeah, maybe I'm right. Actually. There is no. Yes. Okay. So yeah, does the assertion make sense?
Let's assume it does.
Okay. Yeah. Thank you.
You're most welcome.
Yeah. So to do that, we yeah. So yeah. So let's try to prove it. Actually. So to do that, let's consider the Revich homomorphism in terms of maps of spectra. So we have.
Ой, можешь отмотать на слайд назад на секунду? Ага, все, спасибо. Прочту. Угу. Можете дальше.
Yeah, so we have map. So we have first of all, we have X. It is homotopy equivalent to wedge. We have denoted by, well, so this is just sphere spectrum. 0 wedge smash X. We have a map to H. HFP. So this is a homotopy equivalence. This is a map that times identity, where eta is the unit map to Eisenberg-MacLane spectrum. Yeah. And if we apply homotopy groups, so we have this composition, we can apply pi star. Yeah, and after applying pi star, we'll obtain just mod p for Revich homomorphism. Sorry, X. Okay, so actually we just have to describe this map. So consider the induced map of the atom spectral sequences X into the HFP smash X. We have, let's denote this composition by H prime. So we have H prime star from ERST, sorry, to ERST bar. Yeah, so first of all, let me note that homology of the right hand side is isomorphic to AP star times over FP homology of X. Yeah, and from here it follows that the second spectral sequence is just 0 row. ERST, which is a quator over AP star of this homology. I'm sorry, from FP to the homology is 0 once S is greater than 0. Yeah, so sorry. Yes, and the 0 and E2, so here should be 2, 0 something bar is just, yeah, okay, so again, let me write it again. So this is quator over AP star 0 from FP to homology is just homology sorry, so it should be right one, yeah. This is FP tensor over AP star with this. There's no other way to write down. Which is homology of X with coefficients. Yes, so now we can just consider the following diagram. We have I star of X, homology of X with P coefficients. Here, E infinity 0 something, E2 0 something, 2 0 something bar, which is the same as E infinity 0 something bar, which is the same as here. We have H prime star, H prime star. Yeah, that's it. Actually. Yeah, so maybe the one question that maybe I haven't discussed, so that this thing is primitive elements of X. But this is actually clear because of the following description. So the E2 0 something is just FP cotensored over AP star with homology of X. And this is already primitive elements.
Does everyone understand what the square tensor product means and as well as its derived functors?
We kind of discussed it when in computations of.
Okay, so if there are people for whom those two things make no sense whatsoever, please let us know. Otherwise, we'll continue.
Well, okay, so then I suppose we can continue since there is no interruption.
Кстати, первое, вот там изоморфизм, который Иленберг-Маклейн, смеш, гомология такого, оно такое, ну, это, наверное, лучше как-то прокомментировать, да? Тут какое-то расщепление спектра, да, происходит.
Над полем формула Кюнта работает.
Полем работает формула, но здесь написано все-таки, наверное, больше. Здесь написано, что, ну, по-моему, здесь написано, что смеш с Иленберг-Маклейном — это сумма Иленберг-Маклейнов, нет?
Да, но это очевидно.
Ну ладно. Окей.
Well, so yeah, so the fact that homology of smash product with Ehrenberg-MacLane spectrum is free module over Eilenberg over AP star is kind of the consequence of the Kunut formula. So and it works over FP.
Да, может, ты все-таки напомнишь про Котор, ну, чтобы увидеть примитивные элементы.
Okay, so yes, indeed. Let me remind.
Не, ну ты бы то оставил, как бы. Но...
Нет, на самом деле, утверждение про примитивные элементы его проще без всяких которов понять. То есть и то, что лежит в образе Гуревича, это просто образ фундаментального класса сфероида, а как бы на сфере, ну там в категории спектров или где угодно, мы знаем, что гомологии являются примитивными, ну в смысле кодействия алгебры Стинера, да. Просто по соображениям размерности. Поэтому их образ в гомологиях X обязан состоять из примитивных.
Да, но тут немножко больше написано. Но, не, ну, в общем, так или иначе, давайте я напомню. So, let me write it here. So, let me define just cotensor product. So, we have, yeah, so maybe let me define it in this case just. So, we have, what should I write? Yeah, so I have to write something like this. So we have FP tensored over FP with homology X. And then we have two coactions, yeah, on the first factor and on the second one. So we have a map from here to such tensor product. Star homology of X. Yeah, so and this is a difference between two coactions. So this is rho P times 1 minus 1 times rho X. Yeah, where rho is coaction map. Yeah, and cotensor product by definition is just kernel of this map. This is FP cotensor with homology. Yeah, so this, yeah, I can write. This is by definition this one. Yeah, so since the coaction on FP is trivial one, then the difference is just the elements in kernel is primitive elements of homology of X. Володя, стало понятнее или не очень? Могу еще что-то говорить?
Да, хорошо.
Да, ну, то есть относительно первого кодействия у меня элемент 1 тензор x переходит в 1 тензор 1 тензор x. Относительно второго он переходит в 1 тензор ро от x. Ну, вот такие товарищи равны, тогда это, это значит, что ро x есть 1 тензор x. Но это по определению, это определение примитивного элемента. Any other questions?
Да, я вот хотел уточнить все-таки там, где формула Q, на самом деле ты больше используешь. То есть ты на самом деле хочешь сказать, что вот этот изоморфизм с АП со звездочкой тензорной гомологии, как модуль над алгеброй Стинрода, там только левый сомножитель участвует. Ты вот это используешь. Правильно? То есть формула Кюнета, она на самом деле говорит, что да, как модуль над алгеброй Стинрода, тут диагональное действие есть. Но на самом деле утверждается, что оно изоморфно тензорному произведению, где алгебра Стинрода действует только слева. Это такой, все-таки какой-то момент не совсем тривиальный, потому что это утверждение его можно вывести либо из того, что смеш с Эйленберг-Маклейном разваливается в прямую сумму Эйленберг-Маклейнов, или из какого-то чисто алгебраического утверждения, что если ты умножаешь ко-модуль.
Мне кажется, это должно быть следствие коассоциативности, разве нет? Просто что если у тебя есть такое действие, сякое действие, то, в принципе, без разницы, как тебе его.
Ну, это какое-то утверждение алгебраическое. Мне оно на самом деле не очевидно. То есть, что если ты ко-модуль тензорно помножишь на алгебру Стинрода, у тебя на самом деле получается, в смысле, на алгебру Хопфа, то у тебя вот эта штука как ко-модуль оказывается ко-свободной. Ну, я не знаю, мне это на самом деле не очень очевидно. То есть вообще не очевидно. Наверное, это так всегда. Но мне проще это понять из расщепления спектра. Но, видимо, такое утверждение имеет место.
Сейчас. Я не понимаю, мне кажется, это можно просто углядеть из какого-то... Сейчас. Нет, в общем, мне кажется, что это можно углядеть просто из определения, потому что ты можешь там у тебя в определении ты должен взять, типа, отобразиться из HFP в HFP с MHFP, да? Это будет, чтобы получить какое-то действие такое. Сейчас. Короче, сходу я не отвечу, но мне кажется, что ответ там должен содержать слово, то есть там должно Эйленберг-Маклейн, который здесь участвует, его можно переставить с Эйленбергом-Маклейном, который должен участвовать в определении гомологии и кодействия, просто перестановкой там. И это там ничего не меняет, и поэтому вот есть такой изоморфизм, вот как ко-модулей. Вот, там, значит. на котором коалгебра действует только на левом somножителе.
Ну, не знаю, мне непонятно. Ну, давай дальше двигаться.
Ну, в общем, давай поставим. Ну, в общем, я сейчас, к сожалению, ну, сходу я тебе точно не отвечу, в общем. Yeah, so we have kind of described the Hurewicz homomorphism in terms of the mod P Adam spectral sequence. And now we can apply it to proof of Novikov theorem. Yeah, so what actually we want to prove? We want to prove that Hurewicz homomorphism of xi is yeah, so let me maybe denote something like, so let's denote, well, this number by gamma I at the moment. Yeah, I've again used alphas instead of betas. Okay. Yeah, and actually we want to prove that h of xi is up to sign is gamma I times bi, where b is a canonical generator of homology of mu that we have used all the time. Modular decomposables. Is it clear?
Не, ничего не понятно. Вот какое утверждение сейчас доказывается? У нас иксы-то это кто такие?
Доказываю, мы сейчас пытаемся доказать вот эту теорему.
Хорошо. И кто такие иксы-то? Это просто какие-то неразложимые элементы в градуировке фиксированные? Или что?
So, well, so we want, so this is, it depends on which direction you want to prove. So, yeah, so we want to prove that we can take stably complex manifold as a polynomial generator if and only if it is its Milnor genus, or the coefficient on the previous slide is gamma I up to sign.
Yes, and in which direction we goes first? We
Well, go in both directions at the same time. So, so you will see anyway. So we want to prove that xi is polynomial generator if and only if the following holds. So
okay.
this is just reformulation of
Yeah, I mean, do you going to take for xi some abstract generators from Adam spectral sequence description of PMU?
kind of, yes.
Okay. Okay.
Yeah, so we have two cases. Yeah, so first of all, let's consider a case where I plus 1 is p to the power t. Yeah, recall that in the assertion we have two cases where I plus 1 is p to the power t, and the second one where it isn't. Yeah, so let's consider first case where it here -1, and want to consider case when it is not p to the power t.
Да, слушай, а я не пойму, как бы иксы-то они должны прийти из многообразий, да, ну, по идее, или тут как бы, ну, в том смысле, что ты же как бы про класс пишешь, а не про многообразие.
Ну, про класс, да.
То есть ты доказываешь, что есть как бы такой класс, но не факт, что он представляется многообразием, да?
Нет, ну все элементы кольца кобордизмов представляются многообразием.
Ну да. Угу.
Это же, ну, в этом теорема Бантрегина-Тома.
Ну да, понятно.
Ну, то есть я сейчас, в смысле, мы чуть попозже, то есть мы как бы, у нас доказательство в какой-то момент завершится на середине, и мы построим явных геометрических представителей.
Так это нам нужно будет или не нужно?
Это что?
Ну, строить геометрические представители или не нужно все-таки?
Нужно. Ну, в смысле, как бы я сегодня решил чуть упростить для понимания происходящего. И будет...
Ну, я вот про это, да, спрашиваю. Понятно. Хорошо.
Я надеюсь, это будет чуть более понятно, когда доказательство начнется. Я думаю, что какая-то часть вопросов может отпасть.
Сейчас, а еще раз, гамма и т, б и т, это что такое? Ну,
сейчас, гамма и т, вот это, которое 1 или p в зависимости от i.
Ой, ужас какой. Ладно, и т не написался. Да, хорошо.
Нет.
Просто коэффициент, ага. А б и т это кто у нас?
I is, let me just write. So we have homology of mu with integer coefficients, and this is and it is isomorphic to z of b1, b2, and etc. Yeah, so this is in how to. Yeah, so we have alpha i's here, and b i's is just the images of alpha i's under the Thom isomorphism. Я не знаю, стало ли яснее. Но, в общем, это...
Конечно, стало. Так, просто были буковки,
Нет, говорил у тебя ответ. Вопрос.
Не, вполне. А что, нормально.
Окей. Yeah, so suppose now that maybe let's simplify the thing going on. So let's prove the one direction when. So we want to prove that if xi is polynomial generator, then it has such numbers. Yeah. So from this, so we have just described the Hurevich homomorphism, and it implies that.
Да, извини, еще вопрос. А разложимое это в каком смысле, как просто произведение? Или как?
Да, произведение, да, которые вот,
ну да.
в произведении плюсовых частей.
Да, хорошо.
Такие суммы таких произведений.
Я на всякий случай уточнил.
Да, все правильно. Yeah, so we have description of the Hurevich homomorphism in terms of the Adams. So this is a proof. We have this description, and from here it follows that indecomposable element in pi star of x should should be I'm sorry, just one sec. Yeah, so let me state. So I want to claim that h of xi, so if xi is polynomial generator, if and only if, so let's see here. So maybe we will just prove one directions. If and only if the Hurevich image of this element is polynomial generator of subalgebra of primitive elements of MU. Power t minus 1. Okay, so let's see. Yeah, from here it is clear that that if it, yes, I'm sorry, is yes, from here it is clear that if Hurevich image is a polynomial generator, then xi is a polynomial generator in the kobordism. Yep, is it clear? Yeah, because, well, if it isn't a polynomial generator, then it is a product of something, and then the Hurevich image should be product of something in the primitive element subalgebra. Okay, so does it make any sense at the moment?
То есть нам нужно сейчас доказать, что если и такого вида, то xi просто не равно нулю, правильно или что?
Не равно.
Именно по модулю P я имею в виду.
Ну, сейчас, секунду. Вообще говоря, если он...
Ну, то есть мы знаем, что он уже лежит в примитивных, да, и утверждение,
Да.
что гамма и-то равняется единице, это просто утверждение, что это
Нет,
штука.
нет, вообще он мог бы оказаться, теоретически он бы мог оказаться разложимым элементом в множестве примитивных элементов. Как будто.
Окей, сейчас у нас примитивное относительно Стинрода, и там, да, там могло оказаться произведение, хорошо. Ага.
Но, значит, давайте мы, let's try to agree that this direction is obvious. So if h of xi is a polynomial generator, then xi itself is a polynomial generator.
Ну, в смысле, полимерный генератор в описании PH, то тогда x-итый является полимерным генератором гомотопических групп.
Yeah, so this is clear. And so let's agree with this direction, then we will just construct the the geometric representatives with this with such characteristic numbers, and the rest will follow. Okay, and from here, since what?
Ну, все-таки вот просто уточнить. Ну, у нас не может все-таки возникнуть ситуация, что hx это разложимый элемент в этих примитивах. Потому что мы можем... Ну, мы знаем, что у нас Адамс там вырождается, сходится к чему нужно. И если бы эта штука представлялась hx в виде сумм произведений, то мы бы могли наоборот...
Спектралку и понять, да, что он, то есть, что вот эта штука, она полиномиально образующая. То есть вот это, на самом деле, равносильность, она как бы более-менее очевидна из спектралки Адамса. Потому что, ну, если иксы ты полиномиально образующая в бордизмах, то это значит, что он должен быть полиномиально образующий в спектралке Адамса, но это значит, что он должен быть полиномиально образующий в примитивных элементах. Ну, потому что им больше некуда деваться.
Ну, да. Ага. Ну, да.
Поэтому, ну, то есть, на самом деле, я тебя вроде как попытался убедить в том, что вообще равносильность очевидна. Но, в общем, я могу воспользоваться... So I will just use the... Maybe I should say it in English. So actually, the equivalence of these two assertions is a corollary of the of the proof of the computations of the computation of complex Bordian ring, actually. So if you consider just the mod p Adam spectral sequence, then you will see that this guy is polynomial generator in complex Bordian ring. If and only if it is polynomial generator in mod p Adam spectral sequence, and this from this follows that its Hurewicz image is polynomial generator in primitive subalgebra. But so since we are going to present explicit geometric representatives, it is enough to just use the direction from right to left. Okay, and yeah, and from here it already follows that h of xi should be 1.
Все-таки можно повторить, почему hx не может равняться нулю?
Где?
Ну вот здесь, вот с таким условием на и. Почему у меня не может такого случиться, в принципе, что у меня все бордизмы в размерности и, у них по модулю P Гуревич равен нулю. Вот как это проверить?
То есть, ну, надо на спектралку Адамса. Ну, то есть там, ну, в спектралке Адамса она там свободна, у нее там в нужных размерностях есть... ну, потому что вот этот элемент, он отображается в спектралке Адамса в ненулевой элемент. Вот. Но это не нулевой элемент, это в точности там примитивный элемент в этой размерности.
Да, действительно. То есть сейчас у нас отображается он не нулевым образом, да, потому что мы знаем, что Адамс вырождается, он сходится к гомотопическим группам, мы знаем априори, что Гуревич не имеет кручения, значит, это вложение, и поэтому там не может в нуль отправиться. Окей, хорошо. Спасибо.
Yes. Yeah, and we have just we have left case when I plus 1 is p to the power t. but in this case, there is no polynomial generators in primitive subalgebra. Therefore, and this imply from here it follows. So for this case, there is no polynomial generators in P star of mu of P. And from here, so since and again, so here I just have to use the Adams spectral sequence. From Adams spectral sequence, it follows that in this case, H xi is decomposed. So therefore, H of xi is decomposable element in primitive subalgebra. And actually, so and from here, it follows that Milnor genus is divisible by P. Here it follows that corresponding coefficient. So it follows that Si of xi, which is a coefficient coefficient of Bi, is divisible by P. And if we consider the all other primes, then we will see that for prime Q, which is not P, we see that Si of xi is not divisible by Q. And therefore, we know that Si of xi is P to the to some power. In case when I plus 1, if I plus 1 is equal to P to the power T. Something. And we should, and actually the proof is, well, actually we should stop this proof here and present. So now we will present the explicit geometric representatives to prove that there exists such polynomial generators whose Milnor genus is 1 in dimensions I plus in dimensions not of the form P to the power T minus 1, and we will present well, and more or less the same family works to prove that something here is actually 1. So we will present geometric representatives whose Milnor genus is P, and this will end the proof of Novikov theorem. But maybe we should do a break, so because of time reasons.
Да, зачем ты это сказал про остальные куи, как это получить?
Сейчас, ну потому что so for why I said about because for example there might be the case where so we have just proved that it is divisible by p, but maybe it is divisible by some other q, for example.
Ну, раз ты предъявляешь, в конце концов, образующие, то нафиг это надо. Ты же как бы должен показать, что предъявив эти образующим, казалось бы, ты должен показать, что вот P, ну, что ты обязан там, чтобы хотя бы на P один раз поделилось, это да. Ну, как бы ты... Да. Что?
Прав, это возможно, да, это не нужно, если предъявлять симметрических представителей.
Да, а объясни мне, что про другие Q тогда, раз ты сказал.
Ну, я сказал,
да.
что ну, для других Q вот при таких размерностях в примитивных элементах есть полиномиальное образующее, поэтому она должна попадать в нее.
В смысле, я понял теперь, да, что ты сказал. Ага, хорошо. Угу.
И поэтому она не делится на Q.
Да, понял теперь. Ага.
А можно еще раз повторить утверждение про Q? Я вот не понял.
Ну смотри, давай посмотрим. Вот,
ну, что и плюс 1 не является степенью Q.
Ну, короче, смотри, если я посмотрю на примитивные элементы M коэффициентами в FQ, то там в такой размерности есть полиномиальное образующее.
Ну, в смысле, что ты показал, что в других размерностях они есть, а вот там,
да.
где они не могут быть, это только здесь.
Да.
Ну, а значит, на пересечении этих условий пусто. Ну, как бы, окей.
Алексей Геннадьевич, вы с нами?
Семен, значит, как вы думаете?
Нет, в смысле, вы могли отойти, например. Стоит ли делать перерыв? То есть я бы хотел...
Ну, я бы сказал, что априори, да. Well, I think we need to have a break, and well, it's a logical movement to have one. So unless there are any objections or further questions, I suggest we have a break now.
Yeah. So how our break? So it is due to.
Well, I would say let's have a quarter-hour break and then continue.
We'll start at.
Напиши.
Я вот пытаюсь без 20 мы начинаем. Ну или так.
Sorry, it's 2:40, not 1:40.
Ну, я ставлю... Спасибо. Yeah, so we stopped in the proof of Novikov's theorem. So we have proved that, so we have proved first part at all. So we have, so now we know that in these dimensions, polynomial generators are represented by manifolds whose Milner is 1. In the second case, at the moment we know that polynomial generators have Milner genus that is divisible by some power of p. and if you don't want to understand this, it is divisible by some power. It is definitely divisible by some power of p, non-zero power of p, and maybe it is divisible by some power of other prime q. And now we will present manifolds, not many, well, digit manifolds whose Miller genus is 1 or p, depending on okay, so the construction is follows. So consider first the product of CPI times CP. Yeah, just a product of two copies of CP. Well, so two copies of projective spaces, but there is a Segre embedding into CP. Explicitly I plus 1, j plus 1 minus 1. Hope I'm right. Yes. And so preimage of a general hyperplane here is a smooth hypersurface in the product, as denoted by Hij, and it is what is it? It is projective. Well, it is complex projective variety, and so, well, so I guess when I say variety, it is already smooth. So anyway, so it is smooth I2. Well, this smooth I plus j minus 1 dimensional manifold. So yes, so I claim that we can compute its Milnor genus, namely Si plus j minus 1 of Hij. Well, is computable. So let's try to do it somehow.
I suggest we maybe explain the main points and then state the answer.
But do you remember the answer?
No, I don't remember the answer. But let's just briefly say how this thing can be computed. Well, first of all, what do we want? Do we want the tangent bundle or the normal bundle?
Well, it is.
Well, one is obtained from the other, but which one do we want now?
I guess the easiest way to compute its tangent bundle. So it's in terms of tangent bundle.
Well, okay. So we need to compute the Chern classes of the tangent bundle. Well, we know the tangent bundle of CPI, or at least the Chern classes. Why? Well, because if we take the tangent bundle and add the trivial bundle, we get a direct sum of the
hyperplane bundle
of O minus 1, no, O1s. So this gives us the Chern classes. Well, now let's compute the normal bundle. Well, the normal bundle is the pullback of the normal bundled hyperplane by the Segre under the Segre embedding. Well, what's the normal bundle of a hyperplane? So this is the question. This is a question to the audience. Sasha, for example. What is the? Suppose we have a hyperplane in a complex projective space. What's its normal bundle?
What единица?
Brilliant. Well, so we know the answer for the hyperplane. The normal bundle is O of 1. And more generally, if we have a manifold, a bundle, a vector bundle on it, the normal bundle to a smooth zero locus of a section is the restriction of the bundle itself. Well, in our case, the bundle is O of 1. Which gives us a hyperplane. So the normal bundle is a restriction is the restriction of O1. Okay, so so we have the normal Chern class for on the target CP I plus 1 J plus 1 minus 1. Okay, now how to calculate the pullback map in cohomology? Vanya. Как сосчитать pullback при отображении Сегре? Так, вы не молчите.
Ну да, давайте ответим, что надо пересечь с базовыми циклами.
Отец,
Нет, я не подсказываю.
Значит, может, точно все-таки, значит, обучайся, значит, там...
Так я же не рассказываю, я говорю, что нужно пересечь, ну, с циклами на
образующие переходят в парообразующих.
Сейчас, ну, что значит в пару? Она переходит там или в сумму, или в разность, или там с какими-то коэффициентами. Вот как нам найти эти коэффициенты?
Не, ну отображение Сегры классифицирует тензорное произведение, поэтому это просто сумма.
Так, ну хорошо, да. Значит, как нам подсказывает Саша, well, as Sasha is pointing out, the pullback of O of 1 is O of 1 tensor O of 1, which is, well, more or less by the definition of the Segre embedding. The Segre embedding basically is constructed using O of 1 on the CPI, tensor O of 1 on CPJ. Okay, so we know the cohomology map. We know what we want to apply it to, and so we see we get the normal bundle of the pullback of a hyperplane, and then we calculate the Chern classes of this normal bundle, which is basically which we know already. It's C of O1 plus C of O1 on CPI and CPJ. Okay, so we know the normal bundle. We know the tangent bundle of the ambient space. Now we just take the Chern classes of the latter divided by the Chern classes of the former, and we get the answer. Does this?
There is something like I plus J of J.
Okay, so now Semyon is telling us that we have the following exercise. When we substitute all the ingredients in the recipe, we get this answer. And well, this calculation is something we leave as an exercise.
Okay, but yeah, so yeah, let us. But maybe I was wondering, if you want to write something down from your recipe. So,
well, I'm not sure I'm allowed to write on this whiteboard. So maybe
you allow.
I'll get well.
There should be somewhere on. So I don't know if you're.
Well, I'm not quite sure how it works. Semyon, I think it would be easiest if you just write something yourself.
But I'm not sure what should I suppose. What should I write? But yes, we know.
Я не уверен, что сейчас справлюсь с этой задачей.
We know normal bundle of Hij inside of CPI and J. Well, we know it's Chern classes, for example. We know Chern classes of CPI. Well, we know Chern classes of CPI times CPJ. And I guess that's all we need to know. Yeah, and we know that tangent bundle of Hij plus normal bundle of Hij is isomorphic to tangent bundle of CPI times CPJ restricted to Hij. Yeah, and composing all of these, we can get the Miller genus. And if you fix I plus j, then the corresponding, or maybe -1, I'm not quite sure. But maybe it is. So, yeah, and if you fix I plus j, then you'll see that CD of I plus j, yeah, with I plus j is I plus j fixed. Then it is 1 or p. Again, in depending on the sum. So since least common divisor can be obtained as a linear combination of these things, we can obtain polynomial generators as linear combinations of Milnor hypersurfaces. So therefore, sum let's denote it by K, for example, Hij represents class of this manifold, represents polynomial generator of phi star of mu. Yeah, and from this it follows that the divisibility conditions here are exact. So namely, Si is Si of xi is exactly p plus or minus anyway. And yeah, and for one we already knew that. Okay, and yeah, Алексей Геннадьевич, у меня так глобально все. Ну, то есть я не знаю, стоит ли начинать что-то про формальные группы.
Да, я думаю, что почему бы нет. Значит, давайте расскажем хотя бы что-то, значит, какие-то, может быть, дальнейшие моменты на следующий раз.
Окей, ну давайте я, может, с алгебры хоть начну. Там...
Давайте, да, значит, давайте с алгебры.
Сейчас. Yeah, so but let me just say one more thing. So please remember that Hij generates the complex Bordism ring. It will be crucial in on the next lecture because of the our proof of the Quillian theorem would use this fact. So anyway, so yeah, so this is kind of more or less all about the geometric representatives and the geometric representatives for the polynomial generators of Bordism ring. So now we will discuss something purely algebraical, but hopefully it would make any sense. But just one sec. Okay, maybe I should motivate our definition. So maybe you remember that a few lectures ago we have proved something like that. So that if there are kind of homologous theories or cohomologous theories for which cohomology of CP infinity is formal power series with of Chern class, of the first Chern class of the universal bond. This actually more or less the same works for the product of CP infinity and itself. So we have, so suppose we have some cohomologous theory for which this holds, and yeah, and then you can derive from this that cohomology of the product is, formal power series with two generators, star of E, of X, and Y. Yeah, and this implies that actually we can describe a first Chern class of the tensor product in terms of first Chern classes of the vectors. Namely, so we have a map. Actually from the product to CP infinity. This is just multiplication map or the limit of Segre embeddings, whatever we want. So the crucial moment. So this is a kind of pullback of a tensor product. So suppose you have two line bundles over CP infinity, then you can classify their their tensor product, which is again linear line. Which is again line bundle. So we have psi1 tensor psi2. And this map is just this map pullbacks the tensor product. Then there is the following. We have the following question. So suppose we have C1 of psi1, and we have C1 of psi2, and we want to define C1 of psi1 tensor psi2. So, and so since what? Since the second cohomology, so since the second ecohomology of the product is, well, formal power series in terms of x and y, there is a description. So we have a C1 of this guy can be represented as the some aij C1 of psi1 to the power I, C1 to psi2 to the power j. So there is such a description. For example, if E is just Hz, then C1 of the tensor product is what? Саша. Отвечай.
Какой вопрос?
Он написан. Есть целочисленные...
Ну хорошо, C1 к C1 плюс C1 к C2.
This is just sum of their first term classes. And there's kind of so maybe let me present the answer for K theory, then first term class of psi1 psi2 should be something like C1 of psi1 plus C1 of psi2 plus C1 of psi1 times C1 of psi2 beta inverse. So let's go back to the general case. So what do we know about this power series? So consider the following power series. So we have f of x, y is sum of aij, x to the power I, y to the power j. So what do we know about this power series? What can we say?
Ты бы поконкретнее спросил, там, что можно о старших коэффициентах спросить.
Что? Что?
Я говорю, ты поконкретнее спросил бы.
Yeah, so no, well, for example, what can we say about the well, there are some relations on the coefficients. So.
Не, наверное, лучше просто, чтобы яснее звучало, написать, что f x, y это что-то типа m со звездочкой x, где, ну, там, или t, в общем, который является классом, образующим классом в E когомологии.
Может, здесь надо написать не C1, а T. Well, okay, so for example, what is its first coefficient?
Не, ну, кстати, у нас какое определение там ориентации? Ну, то есть там это буквально образующий без... Ну, в смысле, это как бы соответствует единице в классе S0 или просто обратимому элементу. Если единица, то там всегда x плюс y должно быть сначала.
Давай считать, что единица.
Ну да, давай. Тогда там просто x плюс y будет начинаться с x плюс y.
Sasha claims that it starts from x plus y plus something of degree at least 2. I'm sorry. J or I plus j is at least 2. Okay. What else?
И еще эта штука должна быть ассоциативна, потому что m это...
Well, I should claim that there is no so first of all, let's actually I guess the obvious one that it should be symmetric. So f of xy is equal to f y x. Yeah, because the tensor product is symmetric. Yeah, and the part of thing that Sasha mentioned, that f of x0 is just x. Namely, there is no pure powers of x. Yeah, and this follows just from the fact that first term class of the tensor product with the trivial line bundle is first term class of the line bundle itself. Yeah, and the last thing, and this is what Sasha mentioned too, that this should be associative thing. So f of x, y, z is equal to f x, y, z. Okay, so maybe so we have kind of discussed some examples, maybe more algebraic one. So okay, so let's write something examples. So first of all, there is additive one. Yeah, so just f x y sum of x and y. Yeah, all the things here are clear, I guess. Yeah, just because the associative law just means that if you put f, well, instead of y, you put y plus z, you will obtain x plus y plus z. And this is obviously the same as put x plus z, I'm sorry, x plus y instead of x. So second example comes from second example comes from the K-theory. I suppose f of x, y, just x plus y, because there's no way not to write it, and plus ax plus y. I'm sorry, plus axy. It is obviously symmetric. If we substitute y equals 0, we'll obtain x, and it is associative. So maybe we should leave associativity as an exercise. And
Не, ну проще всего перейти от этой группы как единицы минус x, и все. Ну, поменять координаты, типа 1 минус x. И тогда это, ну, 1 минус x на 1 минус, ну, или 1 плюс x. 1 минус x на 1 минус y, минус 1, да?
да. Где-то должно быть а запрятано. Ну, давайте.
Не, ну, корень из ax, да? Ну,
Это просто сотрем а. И...
ну, лучше, да, стереть, а так можно как бы корень формально добавить, да.
This is the same.
Нет.
Ну, не, там не корень, там умножить, а в конце
одно
разделить.
умножить, другое поделить, да.
Не, оба умножить, но просто все разделить. То есть как бы просто координаты расставить.
Да. Точно, спасибо.
Yeah, so and this is, I guess, should be, and this is clearly associative.
Потому что это мультипликативный закон. So it is just multiplicative law. But in the neighborhood of 1.
Yeah. And I guess there's one.
And I think that the formula for K-theory can be obtained this way. You just have to prove that 1 minus x times 1 minus y should be equal to 0. Yeah.
X. Right, 1 minus
something
x.
like that. Yeah, just.
Yeah. I guess. Yeah, and the last one is kind of, I guess it is one of the most important ones, but it's rather appreciated. So suppose we have some ring R, consider its power series, well, consider power series over R, and take some element f from here, such that f of 0 is 0, and its first derivative in 0 is unit in R. Then we can write f of x plus y as follows. Just f inverse. Yeah, so this is formal inverse. F of x plus f of y. So yeah, such thing I guess is called logarithm. Something like that. Yeah, and here is more or less all is obvious. Yeah. Great. So this was examples. So now let's discuss morphisms and stuff. Yeah. So suppose. I'm sorry. So. Yeah. So maybe I should write kind of definition explicitly. So definition is follows. So we have formal group law. Yeah, so this is commutative. One. over R. Well, this is just is F, well, formal power series or R of X and Y with the conditions I've already written down. Symmetric F of X0 is X, and it should be associative. Z, same as F of X. Yeah, so now suppose we have two formal groups, formal group laws over R, then morphism, sorry, F from F to G is power series of one variable with starting with 0, obviously, such that F X Y is G of F X. That would be a rather big one, actually. Yeah, so, and F is isomorphism if A1, if its derivative is unit, and it is called equivalence. If F prime of 0 is just well, 1. Yeah, so yes, we have obtained a category of formal group laws over a given ring. This F R basically of formal group laws over R. Yeah, and of course, yeah, of course, for any map, from R to S induces map from F of R to F of S. Yeah, and the yeah, I guess more or less definition for today is the universal formal group law. So definition, suppose yeah, suppose we have some ring and formal group law over this ring L X Y is called universal formal group law. Yeah, if it maps into any formal group law. Yeah, if for any f x y in formal also of some ring, there exists morphism L from there exists map from L to R such that phi star of the universal formal group law is the given one. Yeah, so the claim is also obvious one. So a claim that the universal formal group law exists. So how should we present such formal group law and such ring? Yeah, this is a question for the audience.
Ну, мы пишем сумма I и G TX в степени I, Y в степени G, и накладываем на коэффициенты нужные соотношения.
Yeah, what is the ring L, first of all?
Well, it's the quotient of the polynomial ring and infinitely many variables by some relations.
So the relations are the following form. So A0J is equal to AI0 is equal to 0, except the first one. Aij is equal to Aj, and yes, there is some relation on of associativity.
I think in the second formula there should be 1 of 0.
Yeah, and yes, it is equal. It's A1. Oh, I'm sorry. I understood. Yeah, this one. Yes. Ij greater than 1. Yeah, and formal group law is just sum f L x y is just sum of A I J X I Y J. Yeah, and there is a theorem, rather hard actually, again, from my point of view. It's hard. I'm not sure that, so maybe early, but I'm not sure how should I write it down. So this Lazar, well, actually it called usually, let's call it theorem due to Lazar, that this ring is isomorphic to free polynomial algebra with infinitely many generators. And let me give a remark here that if we consider graded formal group laws, for example, if we give to x and y degree 2, then this ring in graded case, in the graded case, degrees of xi's is 2i. Okay, and blah, blah, blah. Well, actually, I have kind of run out of things I want to tell, but maybe let me state the last theorem for today, which we will prove next time. So, yeah, so first of all, let me recall that mu is C-oriented homology theory. Yeah, this means that there is class X mu in mu2 of CP infinity, such that its restriction CP1, which is the same as S2, is lies in mu2 of S2 is, yeah, and this is isomorphic to mu0 or maybe P0 of mu. Yeah, and under this isomorphism, it should be 1. Yeah, therefore, there exists formal group law of mu. It's a formal power series over mu y. Yeah, and theorem well, maybe there is one more thing that I want to say. So, and theorem, which is due to Buchstaber, that formal group law of mu is the following, has the following form. This is a factor of sum of hij, xi.
Формула Мищенко называется.
Что?
По-моему, это называется формула Мищенко.
Формула Мищенко это для логарифма.
Ну ладно.
Ну, правда. В общем, тут я R plus R sum of CP S YS. Yeah, so formal group law for mu has the following form. Yeah, so this is a classes of such manifolds. Yeah, maybe so. Yeah, there is 2 more things that so I'll prove next time. Maybe. But this theorem actually has 2 important corollaries. So the first one that note that coefficients of f mu span p star of mu, and we have just did it. Yeah. And the second one is one of the most important results of the cobordism theory, which is Quillian theorem.
Ну, спан это в смысле мультипликативно или как?
Да. Да. Yeah, and Quillian theorem.
In this case, it's better to say generate.
Yes, yes. Generate. Thank you. I start from you. Yeah, and as the second important corollary is Quillian theorem that states that so since this is formal group law, then there should be homomorphism of from the universal one to pi star of mu. This is canonical map that sends f L to f mu. Yeah, so and this map is an isomorphism. Great. Yeah, and this is indeed corollary, yeah, because in coefficients generate pi star of mu, they have the equal set of free polynomial generators. Therefore, this map is an isomorphism. Yeah, I guess. Well, I don't have day today actually.
Well, maybe we should ask the audience if it is clear how the corollary or both corollaries, in fact, follow from the theorem. Vanya and Sasha, what do you think? Is it clear how to deduce the corollaries from the theorem?
Сейчас, в смысле, просто из формулы для FMU, почему следует, что коэффициенты генерируют гомотопические группы, почему это универсальный...
Как из вот этого равенства, которое написано по словам Бухштайбер, следует два следствия?
Ну, по-моему, никак не следует, но может я что-то...
Semyon, in this case, I think we need to explain this point.
Well, so Hij is Milner. So this is the same Hij that was before, which is Milner hyper.
Yeah. First corollary. Okay, I understand it.
Wait a second. Sasha understands it, but what about the rest? Vanya, Mark, Saman, and Vladimir as well, I guess. Do you all understand what is happening?
No, actually, I don't understand right now.
So there are people who don't understand. Okay, so Semyon, I think more explanations are necessary.
But what exactly do you don't you understand? So if you maybe you can simplify my.
I don't understand how you deduct the corollary, the last one from the theorem and the corollary above I don't understand the connection between two of them.
Well, so first of all, we have proved after break that Hij is polynomial generators of, well, the sum of Hij's is sum of Hij's are polynomial generators of pi star of mu.
Yeah. Maybe better to say that modular decomposable, these coefficients of FMU are exactly Hij's.
Yes.
Right. So, so first corollary immediately follows from very first theorem of Novikov, or rather its construction.
Yeah, I can see that. Yeah, thank you. Yeah.
Yeah, and the second one
thanks.
follows from is kind of purely algebraical. Yeah, because so you have a map from two abstractly isomorphic rings that. Yeah, and image of L polynomially generates mu.
Okay. So you use Lazar theorem here.
Yes, of course. So
Okay.
this is Quillen theorem. This is corollary of So using the Lazar theory. Yeah, of course. Corollary.
Ну, то есть это так, типа следствие на уровне, а вот чтобы одно доказать, нужно одну теорему применить, а еще помимо этой, так сказать, чтобы другое доказать, еще другую теорему.
Ну, то есть, да, тут никакого объяснения нет, кроме того, что гоморфизм Фрелича и логарифм для L одно и то же.
Ну, я бы не назвал это следствием теоремы Бухштабера в любом случае. Но просто, давайте утверждение. Нет, как бы.
Let's rewrite. So we have one more theorem that we kind of prove using the facts already kind of know, namely Quillen theorem. And proof, it follows from the combination of Lazar and Buchstaber theorems.
Как и первое следствие, как я понял, или
Нет, первое следствие следует из теоремы Новикова все-таки.
Ну, в смысле, ну да, ну как бы. Не, ну просто как бы если там спрашивать,
я понял.
Понятно, да.
Давай я proposition.
Observation. Не, я бы сказал, что это понятно, но не прямо из этой теоремы. Ну, как бы,
Ну, окей, да. Я согласен.
Are there any more questions on how to deduce what used to be a corollary 1 and corollary 2 from the theorems that we have seen today so far? Sasha, Vanya, Saman, Vladimir, Mark. Well, I don't see anyone else.
Не, ну мне понятно, потому что я это когда-то видел. Но, то есть, мне кажется, это не может быть понятно, вот особенно теорема Введения, потому что
Хорошо,
надо...
значит, это не может быть понятно. Хорошо, значит, ну давайте действительно, то есть здесь может быть, то есть может быть непонятно, но давайте поймем, что именно непонятно. Vanya, Mark, and Saman, and Vladimir, and Vladimir. Are there any other questions on how to deduce Quillen's theorem or proposition from Buchstaber's theorem and Novikov's theorem, and also Lazar's theorem, which is purely algebraic. So we skip the proof. Well, Saman says everything is clear. Vanya, what about you?
It's clear.
Okay, Mark.
Ну, плюс-минус.
Плюс-минус. Значит, Марк, может быть, одно из трех. Или все понятно, значит, или понятно, но частично, или ничего не понятно. Вот что из этого имеет место?
Ну плюс-минус, что имеется в виду, когда плюс, ну, как бы...
Хорошо, значит, что-то понятно, что-то непонятно. Тогда давайте посмотрим на первую вещь, которая непонятна. Где она?
Ее нет на этом слайде.
Так, нет на этом слайде. Хорошо, на каком-нибудь слайде она есть? What about so Mark? If
Хотел спросить, вот выходи, ну.
If it's localizable, let's try to sort it out now. If it's more serious, we'll talk about it later. Значит, Марк, если проблема вот в каком-нибудь обозначении формулы и так далее, значит, которую мы сейчас можем быстро решить, давайте ее решим. Значит, если проблемы были глобальные, то давайте мы ее тоже решим, но не буквально сейчас.
Не, ну я так понимаю, сейчас вы обсуждаете теорему, точнее, не теорему, а средства теоремы
Да,
логики.
мы хотим понять, как вот то, что написано в самом низу, следует из того, что написано посередине. Там принимай на веру, значит, теорему Новикова, теорему Буштабера и теорему Лазера. Okay, well, so it looks like we will probably need to talk about this later. Now, Vladimir, what do you think about all this?
Я прямо сейчас немного отвалился.
Okay, Vanya, is it clear how to deduce what it says in the proposition and then Quillen's theorem from all the other theorems we've seen today?
It's clear.
Well, okay, so Simone says it's clear as well. So I would say well 3-2 is a marginal win. Anyway, are there any more questions? Well, in that case, I think we'll just stop now and continue next week. Well, hopefully at the same time as today. And
let me. But yes, I guess you have a question to the audience actually.
I have a question. Oh yeah, I forgot to mention. Well, it's not just me. I forgot to mention, or more precisely, remind everyone that there are at least 2 possible topics for talks. I would say. A sensible talk plus sensible notes would be a way to get full marks for this seminar. I recall that the topics are as follows. Topic 1 is the Poincare duality for spectra, and topic 2 is the coefficient ring of the SO, meaning oriented Bordism theory. So, in particular, if there are people who would like to understand either first or the second topic in detail, the best way to do this is to give a talk, not to listen to someone else's talk. And so, if there are people who are interested, please let Semyon and myself know. Well, are there any more questions? Okay, well, in this case, I would say let's call it a day.